All right, thanks everyone for coming. So today I'm going to talk about estimating peptide level false discovery rates using target decoy competition. Since I only have 10 minutes, I'm going to give a quick overview of the entire presentation right now with the takeaway messages. So the first takeaway message I'm going to have is that spectrum level, PSM level, FDR estimates are often in practice invalid. So we are going to suggest that instead of that researchers avoid spectrum level analysis and then in fact actually focus on peptide level analysis. After that, we're going to discuss three different variations or three different ways for estimating peptide level FDR. And then we're going to show that they are valid, one. And then two, that methods that compete paired target and decoys often have greater power than methods that don't do that. So what I mean by paired target and decoy is that there's an explicit connection between target peptides and the decoy peptide that the target peptide and the decoy peptide that they generated. All right, so with that, let's go back into a little bit of the background, just to make sure we're all on the same page. False discovery rate estimation in proteomics state analysis is done by using target decoy competition. And what we have here is a set of spectrum, and this is on the spectrum levels, to be clear first. So on the spectrum level, we're going to search it against a target database. A target database consists of peptides that are generally expected to be found in the sample, and then we're going to find the top scoring target per spectrum. Let's say, the first spectrum, we have that peptide with a certain score. We're also going to search it against a decoy database. And a decoy database are generally just peptides that aren't expected to be found in the sample and are generally made by shuffling target peptides. Once again, we get the top scoring decoy and then their score. Then we're going to actually compete them. And this is where the competition part of target decoy competition comes about. So we compete them and we find out which out of the target or the decoy scores better. In this case, 3 out of the 4 spectra that we look at, 3 targets win, and so we're going to keep those, and 1 decoy wins, and we're going to keep that one. So we basically remove any matches that lose out on target decoy competition. Then we're going to calculate FDR with this equation, which is the number of decoys given a score threshold plus 1 divided by the number of target PSMs with the score, with a certain score threshold, where S is the score threshold. That gives us this FDR. We have 1 over 1, 1 over 2, 2 over 2, 2 over 3. And then we make that monotonic to get an FDR threshold. So that's how this PSM level or spectrum level FDR is typically done in practice. We're going to argue here that spectrum level FDR estimates are often invalid. So target decoy competition has been provably shown to control the false discovery rate under 2 assumptions: the equal chance assumption and the independence assumption. The equal chance assumption says that an incorrect PSM will have equal chance of matching to either a target or a decoy peptide. And an independence assumption says that spectra are independent from each other. The proof is shown in this archive paper here, but on spectrum level, for PSM level or spectrum level FDR, the second independent assumption is broken. Specifically, it does not account for the fact that oftentimes that the same peptide will be detected multiple times in a run. So oftentimes they'll say like, oh, peptide X is detected 3 different times confidently by a PSM. And so that, in fact, because of that, these spectra are going to look very similar to each other, and therefore they're not going to be independent. So to show this, we have an entrapment analysis shown here. Due to time, I won't be able to go through the details of it, but we have our false discovery proportion on the y-axis and our FDR on the x-axis. And you see, and for a FDR estimate to be valid, you want everything to be centered around the y equals x line, ideally to be underneath the y equals x line, which is the dashed line here. And you see here, but with our PSM level estimates, we see that it's all consistently above the y equals x line, indicating that PSM level FDR estimates are invalid. So, like I said, we propose that researchers avoid spectrum level analyses and instead focus on peptide level analyses. So next, we're going to talk about 3 different variations on how to estimate peptide level FDR, and then we're going to show kind of what this paired target decoy competition thing we're talking about. So the first method is called, as we're calling PSM only. This is the one that's most commonly found in the literature. So we're going to score our spectra against targets and decoys. This thing on the bottom is a visualization of kind of the results from a score database search that is, we format a little bit different to make it look potentially a little easy to understand, where the rows are spectra and the columns are peptides and the cells are the actual scores. And then there's some missing cells because they weren't actually scored due to precursor thresholds. So in PSM only competition, the first step you conduct is perform PSM level competition. So for each spectrum, you find the best score and remove all the matches that aren't the best score, leading to a bunch of these grayed out matches. Then you're going to take the maximum score per sequence. So we're going to remove the 2.5 score. And then you're going to calculate the FDR on the remaining set of matches. So there's 3 scores remaining, and then we have FDR on the following matches. One thing I did forget to mention just now is that on the columns, we have both black and red peptides. The black peptides are targets, and the red peptides are decoys, and red peptides are decoys. This matters because now we're going to go into the next 2 ones, which explicitly talk about computing paired targets and decoys. And so a reminder, a paired targeted decoy is that for each decoy, we know exactly which target generated it. So there's that explicit matching in there. And so in this table shown up here, table, the first one is the target, and this one after that in red is always the paired decoy following it. So the first 2 are paired, the second 2 are paired, the third 2 are paired, and the fourth 2 are paired. All right, so the second method that we're going to quickly discuss is called peptide-only competition. Same idea, you're going to score the spectra against your targets and then your decoys. But now you're going to first take the maximum score per peptide sequence. So go through all the columns and find the best score, keep that, and remove all the other matches. Then you're going to compete the paired targets and decoys. So that means is you take a look at the first 2 rows, columns, and find the best score, keep that one, and remove all the others. So that means remove the score of 2.1 in the second column. Then we take a look at the next 2 columns. We see there's 0.7, 2.3. We keep the 2.3, remove the 0.7, so on and so forth. After that step, you're going to take the remaining matches and calculate your FDR on that. The final method is called PSM and peptide level competition. And once again, you have your set of scores. But this time, I'm going to first perform PSM level competition, just like in the typical one you find in literature, resulting in this set of matches. Then you're going to take the maximum score per peptide sequence. So go down the columns, take the maximum score, and then you're going to compete the paired targets and decoys. And so this will make us lose the match that's shown in green down in the second column, last row. From that, we're going to then calculate the FDR on the following matches. All right, so given that, I'm going to quickly show you that peptide level FDR estimates are valid, and that and so this is an entrapment analysis. Again, y-axis is false discovery proportion, x-axis is false discovery rate, and you want the lines, these lines to be centered around the y equals x-axis, ideally underneath it, but certainly not consistently above it. And what you see here is definitely that our FDPs are centered around this y equals x line. Next, we're going to compare our 3 different variations of estimating peptide level FDR. The PSM only one in blue is the one that's most commonly found in the literature, and the 2 methods that use this paired competition between targets and decoys are the ones seen in orange and green. So we have here 2 different data sets with the number of accepted peptides on the y-axis and the number and the FDR threshold on the x-axis. And we see that the methods that use that compete paired targets and decoys outperform the method that we most commonly use in literature in blue. And this is for 2 different data sets, E. coli and yeast. We did this for a bunch of data sets. We did this for 5 data sets: castor, E. coli, human, mouse, and yeast, as well as using 4 different score functions: x-score, x-score p-value, combined p-value, and Taylor. And across this, we find that PSM and peptide, that third method that I discussed, that's shown in green on these plots, discovers an average of 17% more peptides than PSM only at a 1% FDR. So today, I quickly showed you that PSM level FDR estimates are in practice invalid. Therefore, we suggest that you avoid doing analysis on the spectrum level and instead do all your analysis on the peptide level. And then I've also shown you that methods, peptide level FDR estimates that explicitly compete paired targets and decoys often outperform methods that don't. I'd like to thank my collaborators on this. I apologize if I ran through this fast because of the time limits, but we do have a bioRxiv paper out if you want to look into more details. With that, I'll take any questions.
I wanted to ask, isn't this method problematic for applications where maybe you want to identify the same pattern multiple times? I'm thinking about quantitative analysis where you want a given pattern to be identified multiple times, so you have multiple points.
So like spectral countings, for example?
Yes, for example.
Yeah, so spectral counting, ideally, I would avoid using spectral counting and instead do something like area under the MS1 curve, or, like DIA, we also do area under the curve of the MS2 peaks, right? So yes, that is a very common way for people who are doing quantification is spectral counting. Unfortunately, because of this, we don't think that it's a great idea. We actually did try a variant that tried to take in account of that information that said, okay, peptides that are highly detected, detected multiple times, they're more likely to be true rather than not. And we tried to take that to account in a different variation that we had, and we found that it actually didn't make much of a difference when you're detecting peptides. And there's a little paragraph about that in the bioRxiv. I don't have the ability to describe how we did it here right now, but yeah.
Thanks.
Yeah, you're welcome.